Hey guys, it's Vince. Today in this video, we are going to be taking another look at an unfortunate CNC failure, once again dealing with a plasma system. Now, of course, as we go through the video, you're going to hear the words cheap being used. And you see that word used in this genre all the time. The unfortunate side to cheap is usually we cut corners. So we'll dissect this video piece by piece for a forensic look. You once again will be set correct in terms of what to look for, and hopefully this will save you a lot of time, money, and frustration. Let's jump right in.
So you're interested into building your own DIY CNC? Good, because I've got the video for you. This is the complete build on my plasma and router CNC.
Okay guys, I hear this from potential clients a lot that they want to cross over plasma cutter to go to a router, and typically a plasma cutter's frame is not designed for the rigidity aspects of a router or a mill. So if you're going to make a hybrid, I suggest you start with a CNC router frame or a mill frame and then convert that into a plasma cutter. It's much easier to do, and the rigidity would be built in already as for it was originally designed. When guys try to do this type of hybrid robot, typically they run into all kinds of issues because, again, transmissions with plasma cutters, they're usually going to use a rack and pinion transmission. The rack and pinions have a lot of variables. You'll see that in this video. We'll cover it. But overall, try to stay concentric on one robot design. It's much easier, especially if you're a novice, to learn. There's a lot more variables with plasma robots, but again, in all fairness, plasma robots typically will make more in terms of size. So if you're running a 4x4 CNC and a 4x4 plasma cutter, you'll typically make more money with a plasma cutter just because of the use of the machine, meaning not a lot of end users or shops have that available. So keep that in mind. You can cut a lot of different metals, and it does it quickly if it's set up correctly.
Being a mechanical engineer, I always refer for the electrical side of the machine as some sort of voodoo magic invocation that makes electricity and commands from the computer move, I don't know, magically, motors and stuff. In fact, for this CNC, it ain't that complicated.
Okay guys, once again we hear this a lot that naturally it's not that complex to do this, and that's an interesting statement because I'm going to attach all of the PDFs from Lincoln Electric, and all they do is manufacture plasma systems. And when you see the grounding process, which is not even covered in this video, it's interesting that a statement like that would be made by someone claiming to be a mechanical engineer. That's a little frightening on my part because as an engineer myself, I can tell you troubleshooting is the majority of what we do. That's all we do, is test, retest, and confirm. So I'm not exactly certain on why he would say something like that, but I think it's all interpretation and making sure you guys understand the gravity of exactly what you're getting involved with. This is a different animal. It's not just creating motion like most routers do. We also have to worry about stability, and the most important thing is grounding so we can achieve that stability.
So with this kind of kit, the computer is the brain. In real time, it will send commands to the breakout board. Then this fellow will send the info to the drives, and that powers up the stepper motor. The breakout board is not your only option. Matter of fact, this is now an older technology. You can now use a controller that has its own chip.
Once again, we are being subject to misinformation. First and foremost, breakout boards are not obsolete. The fact of the matter is he actually posted 3 individual controller converters. Let me explain what I'm talking about, guys. You have up here a USB input, an Ethernet input, and then on this board you have a USB input, and over here on the ESS we have an Ethernet input. These 3 boards all by themselves are useless without a breakout board. Useless. The 3 boards that I'm going to highlight for you, they connect directly to your PC in whatever format they use, whether it be USB or Ethernet, and then take the signals that are received from the PC and then take them and actually go to the breakout board that he's saying is obsolete. So realistically, even though it's parallel port connection, it's still going to be connected to, once again, one of these 3 boards after it actually connects to your PC. So it's basically a middleman between your PC sending the signals. It sends it directly to either the ESS, this board on top, or this USB board, and then it will actually go and send those signals again to your parallel port connected breakout board. The only board that will not have these intermediary boards of the three, any of them, is going to be this Novsum board, which is a USB breakout board in itself, and that's why we see the terminal blocks present.
Okay, let's do the electrical diagram. And to simplify things, I will illustrate only one axis. First of all, you're going to connect your computer to the breakout board using a DB25 connector. Then you're going to power up that breakout board using a 5-volt power supply. Using the same 5-volt power supply, you will connect it to the drive on pulse plus and direction plus. You will then connect pulse and direction ground to some output pins on the breakout board. To give the power to the stepper motor, you're going to connect your 60-volt power supply to your drive. And then, using the electrical diagram from the supplier of the stepper motor, you will connect the correct colored wires to the drive pins A plus and minus and B plus and minus. I cannot tell you exactly which color is for which pin because it will vary depending on the supplier of the motor. Okay, you're almost done here. You're gonna need some limit switches. To connect these switches, one side will go on the positive side of the 5-volt power supply, and the other side will connect to one input.
So do you guys recognize a pattern? If you've watched any of my CNC fail videos, and I recommend you at least go back and watch a few, many of these content creators, what they do is they like to show you wiring diagrams, but they're always missing things. This one's really interesting. He has a parallel port DB25 connector on his breakout board going to the laptop. Well, anybody will tell you, laptops don't have a parallel port connector. And guys are saying, well, you're being technical. No, I'm not being technical. I'm telling you fact that many novice users will watch this video and say, oh, I can use a DB25 parallel port breakout board with a laptop. No, you can't. That's where my ESS or UC400 come in, both Ethernet controllers, which once again would be the intermediary to connect to the laptop and therefore then connect to this breakout board, which once again is required. The other component, many of you already shaking your head who know plasma systems or even my channel in general, know that double shielded cable is required on every CNC robot, namely plasma systems, due to their large amount of EMI produced to produce stable motion. Fact. And all of these diagrams that these guys show never ever show the required cable. We'll see if it's covered later on in the video.
Pin. The limit switches are used to own the machine. You have to understand that when you power up the CNC, it doesn't know where in XYZ the gantry is positioned.
Okay, what he just explained is really not true, and I'm going to show you just how not true it is, because I've actually gotten into debates about this before on my channel, and many end users do not realize Mach 3 has offsets, also known as fixtures. You can call them GPS locations. Whatever you want to actually attribute the name to is fine. The thing to keep in mind is that what you're seeing on the screen slowly coming into focus is the Mach 3 user's manual explaining offsets and how Mach 3 actually will memorize these offsets. If you set G54, G55, and remaining offsets up to actually program in those GPS coordinates of where your table is at, pressing that button to once again activate that offset will set the table in motion to go to those locations after you shut Mach 3 down. Once again, a lot of end users don't think of this, but the guys that do, my more experienced users, they find how fast it is to set up their table to machine from. A lot of guys think you have to use switches so that your table knows exactly where it is. Not true at all. GPS locations are digital based on the DRO settings inside of Mach 3. The question is, do you understand the software enough or are willing to take the time to learn the software enough to really define how to use these in your workflow? The guys, once again, that do it, they get really great benefits and time savings on top of when you incorporate soft limits. That's a whole nother discussion, but this whole thing, you need physical switches. It's arbitrary. Some guys love them. I personally don't. And I've seen so many failures in my years of doing this that I just don't feel a mechanical component is worth the investment when they fail. You can use soft limits. There are certain systems that do require physical switches, but for the most part, they just make a system cost more and attribute to really just making things more complex, especially when troubleshooting is required.
By ohming the CNC, each axis will move until it reaches out its limit switch. You can set in Mark III the limits, which is the maximum distance each axis can travel. By doing so, the CNC will know its working area, and it should prevent some crashes.
Now, it's really interesting he brings up soft limits after he's explaining about using limit switches. And a lot of guys have come to me and said, well, I want to implement soft limits, but I want to use a physical switch too. And what I explain is if you try to use both options, the thing to keep in mind is where you're going to mount your switch and where you're going to set your soft limit. Because ultimately what you're doing is shrinking your table size. I have guys that want to set their soft limit, they think, as a secondary protection against the switch failure. Guys, you do that, you're shrinking your table because, again, it's got to make contact with the switch at some endpoint. So we need to think about exactly in great detail what you're doing. Why an end user would explain using soft limits after he's already discussed using switches, again, it's one or the other. That's the best option for everybody, is to understand how they function and where you really benefit from each. And when you factor in, like I said, soft limits, once they're set up, you heard him just say it, that is correct. It sets the table limits. So if you say you want your table to stop 1 inch from the side, if the table is calibrated properly and you went through axis calibration, it will stop 1 inch from the side and you're set. There's no reason to install a physical switch as long as you have a startup process where you implement setting the soft limit tab. Mach 3 does not do that autonomously. It's probably the one feature I would want changed immediately if I could change it, would be to implement soft limits immediately, and most new screen sets do offer that to where it's active upon you starting Mach 3, and therefore then it really makes switches an arbitrary decision. If you're an end user and you decide to go one way or the other, at least you can test it. I tell all my clients same things: test it first, then decide if you want to make the investment in the switches.
And one last thing, this is the motor tuning and setup menu. This is where you will tune your stepper motors in combination with how your drives are set. This is where you will set the step per revolution. Also, you will set the speed and the axle for each axis. To set the number of steps per revolution, you just have to run the calibration test in Mark III. The procedure is simple. You set a distance, usually it's 1 inch, and you install on the machine a dial indicator. You run the tests and enter the result from your dial indicator into Mark III. It's now calibrated. It's that simple.
Okay, guys, once again, we have to elaborate more on what he said. I'm not saying that the process he described going inside of Mach 3, setting your steps per, and that's based on your transmission, not just the way you set up your drives, but also then going in and setting velocity and acceleration for motor tuning, and the process of doing that after axis calibration. All he said there is correct. But let's go into more detail where he says it's simple to set up axis calibration. It's really not that simple, and here's why. Anyone who's done it usually will tell you this. Let's say you take a measurement with a dial indicator, as he said, of your x-axis arbitrarily at moving 1 inch. Okay, and we can be positive or negative, it's arbitrary, it doesn't matter. The bottom line is, taking one measurement does not produce a calibrated axis technically. You want to do it over a consistent time frame. As an engineer, we always look at the longer the time frame that we can prove something, especially something like motion where we're dealing with tolerances and variables, the longer we can do that, let's say running 100 times of 1-inch cycles to see if you can hit that perfectly, that's when you know you have at least a basis of time of 100 revolutions or 100 cycles. These are things to keep in mind. The other thing to keep in mind is the exponential of tolerance difference based on the size of your machine. I've discussed this in previous videos. He didn't cover this, but I'm going to cover it because it's something many of you need to understand. If you're using a ultra cheap CNC with ultra cheap do-it-yourself type transmissions where we're using, non-conventional components, keep in mind if your chassis is longer than 1 inch, which of course we all know they are, then what you will find is if you have a tolerance of, let's say, 0.003 of an inch variable from the 1-inch measurement you took, meaning you've got 1 inch 0.003 in either a positive or negative variable, and you go the length of the machine, that means for every inch of length, you're extrapolating that additional 0.003 variance over the course length of the machine. Now, if you didn't understand what I just said, replay the video in this portion and really go slow and listen, because I'm telling you right now, this is something that's overlooked, and my guys that typically overlook it are the ones that are buying these machines with these inferior transmissions and wonder why their tolerance over the span of close to 4 feet of a 4x8 chassis is off, meaning all of a sudden they're good at maybe a 11 or 10 inch variable from center and taking their measurements. They're usually okay in tolerance, maybe 2-3 thousandths. As soon as they go way out there on the entire length of the machine, they find that now their variance could be off, over 1/16 of an inch, 1/4 of an inch. If we're dealing with metrics, you could be 6.35, we go quarter, and we'll just keep going up. 12.7. I've had guys be way out and wonder, how is this happening? Well, it's happening because your tolerance, wherever you measure from, unless you're getting a perfectly accurate transmission, which none of them are, you will find that the longer you go from a set measurement, and any tolerance that's there, it will drift, meaning you'll have 0.003 here per 1 inch, but then that 0.003 is multiplied times 46 inches of travel if you have a 4-foot machine. Of course, we're not doing 48 because what we find is that you usually will stop a couple inches before your end stop, or determining factor of where you plan on machining from. Some tables have a little more and give that way, and some tables don't. Now, if you listen to this explanation, you can tell how complex this is, and once again, how fluid it is for me to talk. I get a lot of guys that say, man, you go so fast through this, I can't understand it. Number one, it should tell you 2 things. First of all, I've been doing this a very long time. Second of all, I deal with this on a consistent basis. That's what it should tell you right away. And I'm telling you right now, the guys that miss this level of detail are missing making a machine truly accurate. And the only way to do a truly accurate machine is using a tool like my AccuScale, where once again it measures past 1 inch, because dial indicators only go 1 inch. Typically, some go less than that. You can buy them smaller, but typically they don't go larger than 1 inch. I've seen guys use calipers and other tools. That's not what you want to do. If you really want accuracy over the span of the actual chassis, that's something to keep in mind. And that doesn't mean you have to use that tool. I'm just making you aware of how axis calibration should be done and should be understood, so that when you do get a variable in your tolerance for whatever you're doing, if you're cutting a circle, once again across the span of your chassis, you're not surprised if you see a difference. That's where guys get lost. What, is there something wrong with my machine? Not necessarily. It's just built-in variable of tolerances that, once again, we assemble the machine. It's a robot. Nothing is machine perfect. Tolerances and variables are all over every device that we own. The difference is some are acceptable, some are not. You're doing a production robot. What may be acceptable to some may not be acceptable to you. So understanding this is critical. Once again, if you have any questions, certainly message me, but keep in mind, reviewing this again in the video, play it again as many times as you need. Google search what I'm saying. You will define and see for yourself what I'm saying is extremely accurate.
I will do a test precision later on this video, and it's exactly the same procedure. For the 3-axis, I use Acme rod for the drive system. They are precise. They are within 1/1000 of an inch per foot. and they're not super expensive.
Did you guys see that? Did you see how the Acme nut just slightly adjusted when he started to create motion? And a lot of guys don't think about that. But even though, like he said, his particular Acme nut he bought from McMaster, great place to buy components. The thing is, while the Acme rod may be accurate to 1,000th of an inch per foot, the Acme nut, where it's actually going to be tension with that spring, which is not based on any tolerance, you're basically going to see that slight adjustment being done on that nut every time motion is present, and therefore your tolerance will typically shift. Now, as that spring wears a little bit, it will shift even more, and this is something guys don't think about until after the fact. Once again, they do a preliminary axis calibration, and you should run axis calibration on a new system probably over the course of a month, at least once a week. And the reason I say that, as the components seat themselves, you will start beginning to see wear. The more detailed you are and picking the right components to begin with, you will not see a deterioration in calibration. That's another thing to keep in mind. As parts wear with motion, you may see calibration become inaccurate again. So these are things to always, once again, go over and think about.
I had to get the stepper motor into higher RPMs, and they were just not powerful enough to get the speed that I needed.
Stepper motors are designed for low-end torque. They are not designed for high RPM. That being said, it's always in best practice to actually overshoot the runway, so to speak, with more torque so you can actually give yourself that buffer for those faster rapids. In his particular instance, he's absolutely correct. His Acme transmission just is not what this system needs. So then he's back to the drawing board again to redesign that aspect. Now, guys, think about that for a minute. And when we get to the end and you see the price of this system where it's supposed to be cheap, I really want you to think about how cheap this really is.
So I had two options: get a bigger stepper motor or change the drive system. Guess what? I did both. Yeah, I first bought a bigger stepper motor kit with new drives and new bigger power supplies and everything. It was a NEMA 34 kit with 1200 ounces of torque with 60 volt power supplies, because more volt, more power, baby. Even with the NEMA 34, I kept hearing this sound. Boy, did I hear this sound during the building of the CNC. This is the sound of a failing stepper motor, not enough torque for the RPM it's turning. So I had no choice but to change the drive system for the X and Y axis.
I don't know how many of you out there could afford doing this 3 times, I guess he did it. So he originally purchased his automation kit, bought another automation kit. Now he's got to buy another automation kit. Now, once again, he's a content creator. Let's be honest. He's getting paid to do these videos. However, many of you aren't getting paid. You're not getting paid until you're making products with the precision you require. So you've got choices, guys. You watch people who make videos, or you contact somebody who does this professionally, and whether it's me or someone else, validate them. And I tell you that all the time. You will pay for a consultation with me, but I promise you, you will not be paying for 3 or 4 different automation kits to get your system automated.
Luckily, since I don't need much speed in the Z axis, I kept the Acme rod and the NEMA 23 stepper motor. For the X axis, I bought a timing belt. In combination with the bigger motor, I was now able to reach 850 inches per minute, which is more than I need. I verified the precision with this system, and it was plus and minus 7,000 of an inch, which is okay for a plasma cutting.
Tolerances on your production robot is based on your end user's preference for what components make up the robot and your application. So keep that in mind, guys. He's right. 7,000 is okay for a plasma. It's not great. I mean, typically you can get under 5,000 with the proper transmission, but if his applications are okay with that, then go with it. I always say this to all of my clients. You should not be looking at just okay, in my eyes. If you're paying for a production robot, it should perform like a production robot. If I can get away by doing something by hand, why would I pay for a robot other than to free my time up? The whole idea of a robot is extreme accuracy, repeatability, and consistency to buy your life back, so to speak. AI is doing that all over the place. So keep that in mind. Tolerances and what you're working with your robot can be adjusted based on budget and, of course, what we select for components you're using and the machine itself.
But kind of bad for routing CNC. So I went on a different path for the y-axis and I chose the rack and pinion. The precision improved but was not consistent along the rack. I think that if you buy a better quality rack and pinion than mine, you should have good results. And to build a router and plasma CNC, rack and pinion is the way to go. For both systems, I had to use a timing belt and pulleys. The reason is simple. The pinion was too small to install directly on the stepper motor shaft.
I'm sure you guys recognize now just how complex a transmission can be. He's running belts, then he's going now and working with a rack. The thing about racks, and what he said is true, is that they can be out of alignment. A lot of them can be mounted out of alignment because it's virtually impossible to get precision mounted components that aren't machined in. Think about the repeatability of a robot we just discussed. That's why many of you are buying a production robot. Guys, we can't drill by hand what the robot can do, and you should not even attempt to do that if at all possible. If you need real precision and you're looking to do it in what I would consider a correct format so that you know the tolerances you're working with, then the only way to do that is repeatability. And that kind of repeatability can only be achieved by a manufacturing robot. You're not going to get guys doing jigging that's exact. You're not going to find racks that are typically mounted exact, even if the rack is straight. You go to McMaster Car, you buy a rack that, is of very high quality. It's only going to show how high a quality is, how it's actually implemented in your machine. So keep that in mind as well as far as those level of details, because those level of details usually bite guys. They'll say, hey, I bought a rack and I bought off McMaster. Everything is set. And then they go and do the machining and they find that there's sway in the rack. It might have a buckle in it. It could be the frame is off. I mean, there's so many different variables you're working with. You might have incorrect engagement on your pinion, or you even see here, the rack itself is exposed. So over time, what do you think happens, especially in a non-climate controlled environment? You get surface rust. All of these things affect tolerances. So yeah, it'll definitely increase the speed of motion, but what will it do to the accuracy? Let's stay tuned and see.
Okay, now let's do a quick precision test for each type of drive system. So this is the rack and pinion. Now let's do the timing belt. And finally, the Acme rod. As you can see, the more precise is definitely the Acme rod. So if you're looking to build a precise CNC, ball screw and Acme rod are the ways to go.
You always want to go with a ball screw if your budget allows. Acme screw, guys, is not going to give you most of your performance. Keep that in mind. Look at what he just went through with speed. The other thing that's very interesting to point out is looking at the tolerances that were generated. You saw the belt. You also saw what the rack did, and you saw that your tolerances with both of those type of transmissions, you had variances on both ends of travel. That tells you just how bad it is, and that's without necessarily wear. We don't know how long he's had these components and they've been in service. Think about that, and I've talked about that many, many times. The other thing is, I don't believe it's a fair assumption to say that you're perfect on your Z-axis with the Acme rod when you've only run the cycle one time, which is something else I've discussed. How you would really dictate accuracy, he should have ran cycles 5, 6, 7 times to see, are these tolerances floating or are they consistent? These are things that you find when you're dialing in a machine. Once again, if you're only calibrating to one measurement on each axis, prepare to be really disappointed. I'm just telling you that right now. I have yet to see a machine only require one cycle of travel on any axis to be considered calibrated. You want to do multiple cycles. The more time you put in doing calibration correctly with the right tools, then the better off you are. Because keep in mind, he's using a nice dial indicator as far as it being analog, but the thing is, we don't know if it's set exactly square. It could have a piece of scarf on the block. These are all things that will deter from accuracy and will be adjusted over time. The question is, are you aware of these details enough so that you can, once again, correct these before they become an issue? If your dial indicator moves even a couple thousandths off of being parallel in a vertical format when he's measuring a z-axis, that's enough to give you a false reading in either direction. Keep that in mind.
Of a cheap DIY CNC. If you don't take into account the extra stepper motor kit that I bought and the extra Acme rods, you should be less rich by at least $2,000 for this type and size of CNC.
Okay, guys, this wraps up another video, and I don't know how many of you out there can afford to lose $2,000 and then start over, essentially. Once again, he is a content creator. Like many of them, they're using this for content, so to them it's an investment to do production. He might have corrected it, he might not have. The big thing is many of you are looking to buy a production robot to make money with or to streamline your business. Always look for professionals that can be validated and do it carefully. Use Google, check everything you need to check. And once again, do not eliminate resources that are readily available and free. Google is always available. Stay away from forums who you don't know who you're speaking with. This is something I've said numerous times. A lot of misinformation comes from there. And as you see, a lot of misinformation is spread through YouTube. So once again, please be careful with your hard-earned money. I wish everybody a happy new year. Take care.